Okay, so let's solve one more problem on rotational motion. In this case, we have a total acceleration of point P, and we need to calculate some angular characteristics of the motion, such as angular velocity and angular acceleration of the wheel. Right, so let's split this vector. So let's draw a tangential component. So this is going to be our tangential component. And then we will also draw normal. So this is going to be our tangential component here. Okay, and this here is going to be our normal component. Let's maybe draw it with another color. So this is going to be our normal component, and we can calculate them, right? So we can calculate them. So this angle is 20 degrees, and this angle here, this one here is 70 degrees, right? So maybe it's just here. So again, like I like to use all the same reference relative to the horizontal line. You can do like whatever you like. You can use that 20 degrees angle, so nothing wrong with this. So I just have old habit from the high school. So I always use that 70 degrees when I solve these simple high school problems. Okay, so let's see. So we have our normal component. It is equal to 8 multiplied by cosine of 70 degrees. Let's see how much is that. 8 multiplied by cosine of 70 degrees. So this is 2.74. 2.74 meters per second squared, and then tangential component is 8 multiplied sine of 70 degrees. 8 multiplied sine of 70 degrees, so it's 7.52. So 7.52 meters per second squared. Okay, so we can calculate our angular acceleration. So we know that tangential velocity is equal to alpha multiplied by the radius. Radius in this case is equal to diameter divided by 2. So radius is 0.15 meters. Okay, so then we can calculate our alpha. So alpha is tangential velocity, so it is 7.52 divided by 0.15. Let's see how much is this. 7.52 divided by 0.15. Okay, and this is 50.1, right? So 50.1 radians per second squared, and it is going to be clockwise, right? So we can say that it is going to be clockwise, looking on the tangential acceleration vector, right? So we can use like that right hand rule, for example, right? So to define the angular characteristic. So this is going to be clockwise, right? So this is going to be clockwise. Here we can define like that direction, a rotational direction. So based like on the direction of that tangential vector. Right? Okay, so and we also know that normal component is equal to omega squared multiplied by the radius, and that means that our omega is equal to squared root normal divided by radius, right? that's an ugly square root, right? Maybe draw something better. Okay, so divided by the radius, and this is equal to square root of normal is 2.74 divided by 0.15. Okay, let's see how much is this. So it's 2.74 divided by 0.15, and square root of this, right? So it's 4.27 radians per second. We can't say anything about direction of rotation, so we don't know like where this wheel rotates, right? We only know the direction of acceleration, like, and we know rotational direction of the angular acceleration, but we do not know in which direction this wheel rotates. There is not enough information in this problem to tell. Okay, so that's it. So we can write down our answer. Alpha is equal to 50.1 radians per second squared, and this is clockwise, right? And over omega is 4.27 radians per second, and we do not know direction of rotation, so there is not enough information in this problem to tell. Okay, so that's it. So this problem is extremely straightforward, but there is that small trick, like that we can tell something about direction of rotation for angular acceleration, but we cannot say anything like about direction of rotation of the wheel.